Hello, this is Miss Manasseh and this is my 5th video in my little radioactivity series, and this is about half-life. Half-life is a topic that some students struggle with a bit, but I'm hoping to show you that it doesn't really need to be that difficult. In this video I'm going to try and answer learning intentions 7.11, 7.12 and 7.13. So we're basically going to cover the definition of half-lives, how to answer questions involving graphs and calculations, and then finally just link the half-life to the uses of radioactive isotopes. So first of all, with the definition, it's important with the definition to understand that there are 3 different units that we use for radioactivity, and there's 3 therefore slightly different versions of the definition for half-life. So the first way that we can define a unit for radioactivity is by looking at the number of radioactive or unstable nuclei that are left. So as more and more of those decay, there'll be less left. So the first unit we can use is the number of undecayed nuclei. The second unit that we can use, and this one I mentioned in the video about the experiment, is the activity. So the activity is the rate at which the source is decaying, and it's measured in becquerels, which is number of decays per second. The third unit we can use is the count rate. This is linked to the number of counts that we reach at the detector. So, how does radioactivity change with time? So, as time goes past, more and more nuclei decay, so there are less and less remaining. So if we think first of all about one unit for radioactivity being the number of undecayed nuclei left, if I start off with 100, as more and more of them decay and turn grey in this picture, there's less and less red ones left. So the number of radioactive nuclei which which are left decreases with time. It doesn't matter how many nuclei you start with, you will always find that the number that are left will decrease with time. Okay, so I could have started with 50. I could have started here instead of there, and I would still find that the number of red ones that are left would decrease with time. So when it comes to our half-life definition, this is a 2-mark answer. The first mark is always half-life is the amount of time it takes. For the second mark, you need to tell me it's the amount of time it takes to do what. And the 3 slightly different variants of the definition are just the different units. Okay, so you can either tell me that half-life is the amount of time it takes for half the radioactive nuclei to decay, or you could tell me half-life is the amount of time it takes for the activity to half, or half-life is the amount of time it takes for the count rate to half. So all of those definitions are correct. You need to say this for the first mark and one of those for the second mark. Half-life can take a wide range of values. Some radioactive isotopes have got a half-life of under a second, whereas others have got a half-life of millions of years, so it can vary greatly from element to element. The other thing that I've mentioned is that half-life does not depend on the number of nuclei that you start with. So when it comes to writing an annotation for half-life, we put a T because it's a time, and then half. So if I started off with 4 nuclei, then after 4 radioactive nuclei, then after 1 half-life there would be 2 left radioactive. So that's after 1 half-life. After another half-life has gone past, so when we were at 2 half-lives, how many would be left? Only 1. I could have started off with 8 radioactive nuclei. Then, after 1 half-life, there would be 4 left. And after 2 half-lives, how many would be left? 3. You can keep going with, 2. You can keep going with this to a 3rd half-life if you want. After a 3rd half-life, there would be 1 left, until eventually you've got no radioactive nuclei left. So it's not something that depends on the amount of substance or the amount of nuclei you have. The next thing we're going to have a look at is half-life graphs. So, it doesn't matter how many nuclei you start off with or how long the half-life is, you always get this same shape curve which starts off steep and then gets flatter. You need to be able to find the half-life from one of these types of graphs. I'm going to talk you through the general method. The general method is pick value, any value on the graph, and then read off the y-axis. It's easiest if you've got a graph that goes to time equals 0 to pick that value. Okay, so you can pick this value here. Okay, so pick a value, and what I need to do is read off the y-axis. So here that is 1100. The next thing I need to do is half that. Okay, so 1100 divided by 2 is 550, and I need to find that on the y-axis, draw across, so 550 is here, draw across to the curve, and then I need to read off what time did that take, at what time. Okay, so then I'm going to draw downwards to there, and this value here is the half-life. So first of all I'm going to read off the number, which is 6, and the unit is minutes. So then I need to find that on the y-axis, and then 4 is draw across to the curve and then downwards, and 5 is read off the number and unit from the x-axis. So I'm going to give you another couple to have a practice. The only other thing I was going to show you quickly is, look, it doesn't matter which value you start off with, so I'm going to pick a different start value. If I pick here, I'm going to pick 400 because it's one that's going through the grid line. I could have picked this value on the graph, go across to 400, halve that, and we get 200. I'm going to go across to the curve and then down. Now how long did it take me to go from 400 to 200? Should be exactly the same. I've actually misread the graph slightly, I think, but it's giving me 7, but I should have about 6. So have a go here. Source A is a little bit confusing because you can't see the initial dot, so maybe try source B. Okay then, so starting off with source B, the original value is 120. Half it to get 60. Draw across to the curve and down. The answer is 20. The unit is seconds. So for source B, it is 20 seconds. If you did do A, the starting dot is underneath that one. Half it again is 60. If you go across from 60 to curve A and then down, that one has got a half-life of 5 seconds. One more example. Again, pause the video if you want to see how you go first. So the starting value is 80. Half that to get 40. Draw across to the curve and then down. The half-life is 2 and the unit is days. Okay, so that is half-life graphs. Next thing is, we're going to look at some different calculations. Okay, so again, I'm going to go through one example of each. You might want to pause the video and have a go first before you look at the solution. So, polonium-216 is down here. It's got a half-life of 0.15 seconds. What proportion are decayed after 0.6 seconds? The first thing I need to do is look at how many half-lives have gone past for the question. So the half-life is 0.15 seconds. I want to know n, which is how many half-lives. So what I've got to do is take 0.6, the amount of time I'm interested in, and divide it by 0.15, and that's telling me that there are 4 half-lives have gone past by the time we get to 0.6 seconds. So how do we work out the proportion? Well, if we start off with 1, we've basically got to half it. 1, 2, 3, 4. There are some slightly more sophisticated methods that you can use, but I find this leapfrog method is quite foolproof. So there were 4 half-lives, so I need to leapfrog 4 times. So after one half-life, there would be half left. After another, there would be a quarter left. After another half-life, there would be an eighth left, and after another, there would be a 16th left. So the answer to this question, the proportion of undecayed nuclei left after 0.6 seconds is 1/16. Example 2. Protactinium has an activity of 200 becquerels and a half-life of 70 seconds. Oh, that is one that is not on here. What will the activity be after 3 minutes and 30? Okay, so the activity that we're starting off with is 200 becquerels, and we've said the half-life is 70 seconds, and we're interested in this time, which is 3 minutes 30. So the first thing I need to do is to get that into seconds. So 3 minutes is 180 seconds, add 30 is 210 seconds. So then I need to find the number of half-lives. So that's going to be 210 seconds divided by 70 seconds, so 3 half-lives. So in terms of our leapfrogs, 1, 2, 3, this question is not about proportion, it's about the activity. So in the beginning position here, I'm going to put 200 becquerels, and then I've got to halve that 3 times because 3 half-lives have gone past. So after one half-life, it would be 100 becquerels, after another it would be 50, and after another it would be 25. So the answer to this question is 25 becquerels. Next question is very similar. Radon has an activity. Oh, I've missed out the I've messed up the wording here. This should be, it should tell us how many undecayed nuclei there are to start off with. So let's go for a radon sample has 6,400 undecayed nuclei. Oop, spelling error. How many would be left after 11.4 days? So this time we're interested in the number of undecayed nuclei. That starts off at 6,400, and we are interested in radon 222, which has got a half-life of 3.48 days, and we're interested in time equals 11.4 days. So the first thing we need to do is work out how many half-lives that's going to be. So we've got 11.4 days divided by 3.8 days is going to be 3 half-lives. So we're going to leapfrog 1, 2, 3 times. We were starting off with 6,400, so after one half-life, half of that's going to be left, so 3,200. After 2 half-lives, 1,600, and after 3 half-lives, just 800. So the answer there is 800, and the unit is nuclei. Example 4, this one's a little bit harder. It's probably harder than most of the things I've seen at GCSE. So if I find a 90-year-old sample of cesium-137 with 5,000 nuclei, how many were originally in the sample? So this one's a bit different because instead of looking at a point in the future, I'm going backwards to how many there were originally. But the general method is still the same. So it's asking me about cesium-137, where the half-life is 30 years old. So the half-life is 30 years. This is asking me about saying now it's 90 years old. So how many half-lives have gone past whilst it's been alive? So the number of half-lives would be 90 years divided by 30 years, so that's 3 half-lives. The difference with this question is, instead of us looking at a point in the future, we're looking at a point in the past. So if you go back this time we're going backwards, and we know that currently there were 5,000 undecayed nuclei. So one half-life ago there must have been twice that many, so 10,000. 2 half-lives ago we can double it, it would be 20,000, and 3 half-lives ago there would be 40,000. So originally there must have been 40,000 nuclei. It's very rare at GCSE that they would give you one like that, but I thought I might as well show you just in case. So that's pretty much all of the different calculation styles that they can give you. The final little bit then is to talk about how half-life affects its use. So if we think about something like this, which is where we're using beta decay for calibrating foil thickness, it's going to, once you've kind of, and you've got, if you remember how this works, you've got your radioactive source on one side and your Geiger-Müller tube on the other side. You need to have something that's going to be giving out quite a constant rate of alpha, beta or gamma, probably beta, because otherwise you're going to have to keep recalibrating this machine often. So what you would want for this machine is something with a very long half-life so that you don't have to calibrate it too often. As a contrast to that, if you think about the use of radioactive isotopes in terms of in the body as radioactive tracers, you wouldn't want the body to stay radioactive for a really long time, okay? But you need them to stay, remember the way that you get tracers into the body is you either inject them, you ingest them, so eat them, or you inhale them. Whichever method you use to get them into the body, you need them to last long enough to get from where they're made to the hospital and into the body, so a couple of hours at least. So these have usually got a half-life of a few hours, so long enough to get them inside the body, but within a day, if you think of how many times you can halve, how many sets of a few hours there are in a day, it would basically go down to 0. So I think we've covered everything. So we've talked about the fact that radioactivity decreases over time and activity itself is measured in becquerels. We gave a definition for half-life, and we talked about the fact that it can be very different for different isotopes and linked that to their use. And we've done simple calculations on activity, both using the numbers methods and graphical methods. So that is everything you need to know for half-life.